Hi everyone, so we're going to do another example of an addition of hydrochloric acid to an alkene. This time maybe just a bit more substituted, okay? Slightly more complex structure. So we have 2-methylpropene today. So we have 3 carbons and our longest carbon chain plus a methyl group there. And exact same, so always starts off the exact same way. So identifying where our electrons are, because that's how we know where things are going to start moving. So our double bond, we know we have some pi electrons here. This isn't really the normal convention here indicating or drawing your pi sign out, but for you, just so you know that it's actually there, okay? Now, so between our hydrogen in this bond, there's an electron being shared by the hydrogen, and in the chlorine there's 7 in its outermost valence, so we draw those in blue. So there's 1 here being shared with hydrogen, then there's 2, 3, 4, 5, 6, 7. So 7 electrons in the chlorine. Again, now we look at polarity, okay? So where is there a difference in electronegativity? And we know by now that chlorine is more electronegative than hydrogen. So chlorine gets a delta negative sign while hydrogen gets a delta positive. And again, we know all of this, but we're going to recap so we're completely sure. Chlorine, being more electronegative, is going to pull those electrons closer towards itself, and this becomes important when the bond between hydrogen and chlorine is broken. And that's what's going to happen now. So the pi electrons here are going to interact with that positively or slightly more positively charged hydrogen. And by moving our curly arrow here, we show a bond is forming there. Hydrogen can only have 1 bond, so it's going to break its bond with chlorine. And chlorine, being more electronegative, is going to steal that red electron. Okay, so we'll see in a while that chlorine, in addition to its own 7 valence electrons, it's going to have 1 additional one. So because it has 1 new electron, it's going to have a formal negative charge. So we'll see that in a little bit. But our most important step now is identifying where, okay, or which carbon on either side of that double bond is that hydrogen going to go. So we'll do that step next. So we draw out both our possibilities. So our double bond has been broken here, and we can have one of the 2 possible outcomes. So we can either have our hydrogen going to the carbon on the right hand side. I'm just going to pop that in blue, so I'm just going to highlight that here for the moment. So it can go here. So draw out everything. Pop our hydrogen here. We'll actually just pop that in red so we can keep track of it. So it can go there, and that would mean then the carbon on our right hand side here becomes our carbocation, and we can put that in a positive symbol there. Now our carbocation, and just so we're confident there, our carbocation is this one. It's the carbon with the positive charge, and because that's only bound to 1 carbon directly, that is a primary carbocation. And we know when we compare primary, secondary and tertiary, this is typically the least stable. Alright? We can also, on this side, we can have our hydrogen join up on the right side. So drawing the 2 hydrogens are already there. So our hydrogen can go here. We fill in the rest of the structure, which would make this carbon on the left hand side our carbocation. Because this carbocation here, highlighted in red now, is bound to 1, 2, 3 carbons directly, that becomes known as a tertiary carbocation. And if we're to compare a tertiary to a primary carbocation, we know that this is the most stable. It's the most energetically favourable, and this is the one that forms. And again, we can highlight this in a big red box, so we know this is the one that we're taking to our next step. So we continue on. So although our structure has gotten a little bit more complicated, the steps and the rules still stay the same. So our carbocation now has been identified, and our hydrogen was added to the carbon with the most hydrogens there already, as per the Markovnikov rule. We bring back our chlorine that we dealt with earlier. We show its valence electrons there that are available, and we show the electron that it stole from hydrogen earlier on, and we show its negative formal charge. And now our negatively charged chlorine, is going to, these pairs of electrons are going to be moved towards our positively charged carbocation. And it's really, really important that you show that full arrow, okay, so beginning from our electrons all the way to where we actually wanted to end up. There's no point showing it ending up in the middle of nowhere, in the middle of empty space, because that does not show accurately what is actually happening, okay? So keep that in mind. So when we do that, we end up with a product. So we draw everything out again. So we have our hydrogens here. We have our red hydrogen from earlier. We have, excuse me. We have our hydrogen from earlier, we'll do that. And we have our methyl groups here. And we have a chlorine group here. So same as always, identify your longest carbon chain. So 1, show it here, 1, 2, 3. So again, we're still dealing with something with prop, P-R-O-P in it. We have an alkane, so we're having propane. Our chlorine and our methyl groups, okay, we pop those in blue here. They both are on carbon number 2. So again, 1, 2, 3. So we are going to have, do this in red, we are going to have two chloro, 2 methyl propane. And that's the most stable product, and the product that will be generated or produced in the highest proportion in the lab. So if we zoom out again, we can see our full reaction mechanism here. So again, we've started off with 2-methylpropene. We have identified where electrons are. We've identified what is more electronegative, what is more electropositive. We've shown the movement of electrons through our curly arrows. We've identified 2 possible carbocations that could be produced here. So which carbons the hydrogen is most likely to go to. We've used a Markovnikov rule to identify which is the most stable. And we know our tertiary is the most stable in this instance here. And because it's most stable, it's most energetically favourable, that'll be the one brought forward in the reaction. And that's going to interact with our now negatively charged chlorine to generate 2-chloro-2-methylpropene. So as always, give it a go yourself, try and explain it to yourself or to your friends out loud, and see how you get on.